Careful. Everyone, don't breathe too much. Yeah, okay, that only took 7 minutes. Great. So we'll do that in geometry. Anything I can do for you all today? Any questions over anything you'd like to chat about? I got more. I want to talk about eigenvalues, eigenvectors today. But is there anything up till then that you would like to talk about? Okay. Cool. And everybody saw that I will take exam corrections up till Friday if you need them. So maybe just let me know if you're going to do that. And if you do, please get them, just put them in the thing outside my door by noon, if possible, on Friday. If you need more time. And Evan, I got yours. Found them. Thank you. All right. Onward. So, let's see. I just want to see where we might have left off. We got to determinants. We were talking, I think, about the geometric aspects of transformations, or did we not quite get there yet? Is that right? Evan's giving me like a subtle nod, doing the ASL, yes. I had to, when I worked at IBM, before I got here, we had an intern for the summer, and she was hearing impaired. And I guess deaf is actually like the term she used. That's a cool term to use. But I tried to learn ASL the entire summer, and the poor person she was just like, can we just write? Just like trying to, my ASL was so pathetically bad that she was just like, I don't know what you're saying. I think I need some training, not just winging it. Okie dokie. So let's take a look at a matrix. Because I really, my goal today is to get through eigenvalues and eigenvectors. So let's just start with that. Eigenvalues and eigenvectors. And that word eigen is it's a cool word. These are sometimes also called, instead of eigen things, characteristic things. So that's a thing you can equate with eigen in these statements here. The heart of all of this is understanding that a matrix can be viewed as a function that transforms the plane into a new space, just transforms everything in the plane through stretching, rotation, and flipping. So if you're in my geometry class that follows after this sounds pretty familiar. Stretching, rotations, and flipping. We're not going to get as heavy with it, but let's just say given a 2x2 matrix A, let's see, it looks like this. We can view it as a transformation of the plane. So I'm just literally writing down what I said, making it formal. So remember, R2 stands for the plane because you have a real line and another real line, and those are orthogonal to each other. So in here, I've got vectors, and I've got, let's say, a vector that ends at the point x1, x2, and so I would denote that vector like this. Once you know the tip, you know the vector, you just have to think this vector has extra information. It's pointing toward that point from the origin. All vectors really should probably be thought of as stemming from here. You can think of it in other ways, but for us, everything's going to stem from the origin here. So we create this transformation, so T, that takes a vector. So I'm thinking of this kind of like a function. This is T of this vector is defined to be the matrix A times that vector. And when we, I'm going to want it down in a minute. When I multiply this through, it's this row dotted with that column, so I'm also reviewing a little bit. So I get AX1 plus BX2 as the first row here, and in the second row I get CX1 plus DX2. And that's a new vector. So what happens through the matrix multiplication is this thing here gets transformed into a new one. So let's just pretend it lands over here. We have no idea. It could be anywhere. We could make it go anywhere by picking the right A, B, C, Ds. But over here, I'm just gonna put A times X1, X2. And that's that dude right up there. This is T of X1, X2. Our goal is, given a matrix, given a 2x2 matrix, to understand how everything in the plane gets transformed in some way. And the way to understand this is to get to the heart of the matrix. So these things right here are the skeleton. Let me not say heart. These are the skeleton of the transformation. So we're gonna find the bones. We're gonna talk about how to find those bones, what they mean, and then how to use them to understand what is happening a little bit more. I gotta take this off. When I put this outfit on this morning, my wife Amy's like, boy, you sure look gray today. It's a lot of gray. It's like, come on. Watch the man in gray. All right, so let's take a look at some examples. And in fact, let me grab a couple examples I whipped up before class. Here. Oh, these aren't the examples I whipped up before class. Yeah, but they're good enough examples. They're good enough. So let's say I've got this matrix A that is 3, 2, 1, 4. Oh yeah, this guy's gonna be super, super happy. I wanna keep my little secret notes up here. I already found the skeleton. I exhumed the skeleton and I got it right here. But we're gonna get to it in a bit. So let's think of this thing as a transformation. It takes a vector x1, x2, and we're gonna multiply by that. And sometimes it can help to just work this formula out ahead of time so that we see what is going on. So it's gonna be 3x1 plus 2x2, and then 1x1 plus 4x2s. So let's do a few computations, and let's have here our input plane, and then let's make an output plane. So we can really keep these things organized. So the first thing, I'm just gonna pick a vector and plug it in. Now, I'm gonna pick one very special one. I'm gonna take the vector 1, 1. So 1, 1 is the vector we're going to plug in. Could you do me a favor and find the output? Write my little secret down. Scratch, maybe we'll do some scratch right here. What'd you get out of that corner?
I got it was the vector 5, 5.
Does that sound right to everybody? 5, 5, awesome. If you didn't get that, let's talk or double check your work, because we're just replacing these two numbers with 1. So you get 3 plus 2 and 1 plus 4. So the output vector is 5, 5. Let's pretend that's 5 there, and that's 5 there. Let's give this guy a name. Let's call this V1. And then this vector here is T of V1, and it is equal to 5, 5. Anything interesting to note? Taking someone on a tour, you brought someone to class, you're like, oh, hey, I wanted to show you this. Why is that? What's special about what just happened there, Corbin? Yeah.
Linearly dependent.
Totally linearly dependent. They literally point in the same direction. Right? Do you see that? So check this out. This one has a magnitude. The length of this is actually square root of 2. You could see that with the Pythagorean theorem. So 1, 1, right triangle. The length of this one is 5 square root of 2. So let's actually make a little note here that the length of this vector is 1, square root of 2. That's its length. The length of this one is 5 square root of 2, if we were to measure it. And the direction is the same. This is 45 degrees. This is 45 degrees. So the same direction is expressed, but a different magnitude comes out. Let me stop. Does this make sense? Yeah, we're good? Okay. So that's kind of interesting. It took this vector and didn't really do anything to it except scale it. Let's try another vector. Let's try somebody right nearby. What about 1, 0? So let's call V2 just 1, 0. In other words, the horizontal component of that vector, where's that going to go? Take a minute. Find that, please. Something a little different happens, right? What is T of 0? Get out. Evan, what'd you get out?
3, 1.
3, 1. Everybody cool in getting 3, 1 out? Yep. Okay, good, good, good. So when I plug this one in, something different happens. It's not the behavior we just saw in terms of direction and magnitude. This one changes its direction and magnitude. So the output of this one, get rid of our little angles here, goes to 3, 1. So let's see, that's 5, that's probably 3, and that's probably 1. So the output is right there. So that's T of 1, 1 right there. That's T of V2. Let me use the same notation. T of V2 is just 3, 1. So this thing that we witnessed the first time doesn't always happen. But when it does, it's notable. It's a special event. So let me say this, I'm going to say this 500 times today. This is an eigendirection because when I transform it with this matrix, the direction remains unchanged. It's a characteristic direction. The direction is not altered by the transformation, only the magnitude. This, when I run it through, gets stretched and rotated. This one only gets stretched. Let's try another one. Let me just pick one at random. Could you please try this one? -2, 1. So let's call that V3. What is T of V3? So yeah, so V3 is, just in case you can't read my semi-poor uniting. And then see if you notice anything interesting about that. I really need some chapstick. The one thing you should never loan anybody or borrow from anybody, especially if you're a germaphobe. Son of a gun, I got none. It's all right. Lou, you got that one cranked out?
I hope.
Cool. I hope so too. I like it. If you did, I would still love you.
-4 and 2.
-4, +2?
Yeah.
Sounds good to me. Sounds exactly like what I would expect. So when we take t of -2, 1, as Lou provides to us, we get out -4, 2, just like that, right? Did you happen to notice anything interesting about the output and the input?
It is a multiple of 2.
Yeah. So again, the direction didn't change, just stretching by a factor of 2. So when we plot this guy out over here, 2, 3, 4, 2, we notice that once again, t of v3 is actually, now I'm going to write this out in a different way. It's equal to -4, 2, but I'm also going to write that like what Lou just gave us. That is 2 times v3. Now it's just twice the original vector. And over here, I can't do that with this one, but up with this one, this is equal to, remember v1 was 1, 1, and I've got 5 times it, so this one was 5 times v1. The vector encodes the direction and the magnitude, and the only thing getting changed here by this transformation is the magnitude on those 2 vectors. This is another eigenvector. So this, and in some ways it's better to think direction, because if I pick any vector in this direction, it's just going to get multiplied by 2. If I pick any vector in this perfect diagonal, it's just going to get multiplied by 5 in length. Stretching here, stretching here. What happens if I come down here? Let's try one down here just to make sure that we're seeing what is true. So if I had -1, -1, and I ran that through, t of -1, -1 is going to equal what? What does that turn into? Can you help me out with that?
-5,
-5, very nice. Thank you, my friend. So that's actually 5 times the original. Scales it by 5. So in this direction, we also have stretching. Look at how the stretching occurs. It's away from the origin. So these eigendirections, let me write this up so you got something nice to put down. Do I have an eraser somewhere? You don't know, do you? Did you see it somewhere? Did someone say something? I'm just hearing things.
No, I said it was in there.
Thank you, thank you. Do not do that to me. Do not leave me hanging. Nobody said anything. Remember that old man you saw in the camera?
What old man?
Yeah. Yeah, what old man? So, notice how the directions 1, 1, or excuse me, 1, 1, and -2, 1 remain unchanged by the matrix. They are only scaled by a factor of, what was this one? Was this 2? 5, thank you. By a factor of 5 and then 2 respectively. This is the hint for how we're going to find these for every single matrix. So every 2x2 matrix has these things that form its foundation, that tell us how it acts on the plane, and they are called eigendirections. The eigenvalue is the scaling factor. write that out. So every 2x2 matrix has one or two eigendirections and corresponding eigenvalues. In the sense that if I have a 2x2 matrix, A, B, C, D, so let me put IE here, times V1, V2, that is scaled if I pick the right V1 and V2. So that's a lambda, that's just a scalar, so it's a real number. And what we just saw is summarized here very loosely like this. So let me stop for a second and let you finish writing and processing, and let me know if any of this needs clarification, because I'm going to do a bunch of examples. Yes, sir.
Is eigendirection the same as eigenvector?
Yes, thank you. Yeah, good stuff. So this is eigenvector. Thanks, Carmen. Yeah. These characteristic directions, these are the skeleton of the transformation. So for this guy here that we just had for 3, 2, 1, 4, I would say this has eigenvalue lambda equals 5 and corresponding direction. So we got a scaling and direction and vector, eigenvector. And you can also call this eigendirection if that feels better. Eigenvector 1, 1. I could use anything I want here as long as it points in the same direction. So that could be 2, 2. That could be -1, -1. As long as it's in that line through the origin, you're good to go. The same line through the origin. And it has eigenvalue lambda equals 2 with eigenvector -2, 1. So like, how are we gonna get at this? Because I worked this backwards. I set up what I wanted and then pretended like I didn't know, and then we found it through happenstance. But how do we get at that? And the key is this, right down here. So how to find the evals and evacs. And I'm going to give you a nice algorithm. There's some cases that are weird. We're not going to get into them, but we're going to get into the stuff that will matter for us as we move forward. So, given a 2x2 matrix, given A equals A, B, C, D. It's a very, very well-defined plan. We're going to set A times, and you can use x, y here, or x1, x2, or v1, v2. Let's just say x, y, and practice all sorts of different ways of writing this. Set A times xy equal to lambda times xy. What we're going to do is find the xy and lambda that make this true. Find the lambdas, and xy directions, and actually put here, put corresponding in there because they pair up, corresponding xy directions that make this true. We're looking for only the places that get scaled with no directional change that make this true. Okay, so this is going to get a little linear algebraic, and then we're going to come back to a nice solid way of getting this rocked. So, get up. All right, so this becomes, so just a word of warning. I'm giving you the steps for how we're gonna get to a sweet way to find this, so I'm explaining it. You're not gonna actually write this out. This is just the flow for understanding what we're gonna write out to actually get this stuff. So this becomes let's put A, B, C, D. Let's replace A with what it is, times X, Y. And I'm gonna subtract this off. And over here, I've got 0, 0. Because everything here, this is a vector equation. There's actually 2 rows here that are being encoded. This one here, I'm gonna rewrite. So this is A, B, C, D times X, Y minus, now I'm gonna pull this lambda out in front, and I'm just gonna put the identity matrix right here. So notice this is just the identity matrix. It doesn't change anything. If you take this times that, you just get XY. You might be wondering, why did I do that? The next step should show. I'm going to pull this out, so I'm gonna factor this XY out. So this becomes A, B, C, D minus lambda 1, 0, 0, 1, parenthesis. So that's all in parentheses, times good old XY equals good old 0, 0. I got 2 more lines I'm gonna put up. I'm gonna take this lambda and multiply everything in this matrix. When you multiply a matrix by a scalar, it's just like multiplying a vector by one. This hits everything in there. So this side becomes A, B, C, D minus lambda 0, 0, lambda. I've got X, Y equals 0, 0. And we're just about done. I'm gonna combine these 2 matrices. So to add or subtract 2 matrices, you just do it element-wise. So my new result here will be A minus lambda, B minus 0, C minus 0, and D minus lambda. And then I have that times X, Y equals 0, 0. All right. Off the top of your head, can anybody come up with an XY that works there? What you got? What do you think? I thought you did something, so I thought you made a gesture. Can somebody give me an XY that works there? 0. There we go. Beautiful, Trayson. Yeah, exactly. So notice that if I just let X be 0 and Y be 0, this works, right? So good eye. That's not very interesting, and it's not a direction, it's just the origin. So what we're interested in is, when does this have a non-zero solution? When does this have a non-trivial solution? So this equation has a non-zero vector solution. Well, my pens are just cashing out today. Grab some. I bet in this bag there's some good stuff. There we go. Has a non-zero vector solution if the determinant of that matrix, oh, that's lovely. Things got really, is equal to 0. If that determinant's non-zero, this has a unique solution, and we know what that solution is. It's 0, 0. So what we're actually interested in is what lambda values make this matrix singular. So we will now find the lambda values that make this true. Once we find those lambda values, we'll find the corresponding xy values that work with them. So, could you just take a second and see what you remember? Can you crank this determinant out for me? This is determinant of this thing. See if you remember how that works, and if you don't, that's okay. It's been a while, or maybe never. That's totally cool. This gives me some chapstick finding time. Jerky. Looking okay. Just on the most superficial level. I didn't do any algebra yet or anything. I took b times c and put a negative in front of it. So you take this product to the left and make it negative. How do you remember that? Well, the negative numbers are on the left of the real number line. That's how I remember it. So negative product, positive product this way. And it looks like this. And we're going to set this equal to 0. So now I got an equation. It's about to get really beautiful too. Is it really? It looks less appealing than it's about to look. Let's FOIL that sucker out. Get that. So that's a FOIL. And then notice these lambda terms can come together. And I'm going to rearrange this. I'm going to put lambda squared first, plus minus a plus d times lambda. That gets me these dudes. And then this thing here, this is all just constant stuff. So I've got plus AD minus BC equals 0. Pretty, really pretty. And it's about to get prettier because we're going to name some stuff. Or we're going to see some stuff. So look at the original matrix. Let me put it up here so you can eyeball it. So the original matrix looked like this. And let me stop and let everybody get caught up, but I'm going to ask you, do you recognize any quantities associated with that matrix here? Cormac, yeah, what are you seeing?
The determinant is AD minus BC.
Right on, here's the determinant right here, right? A times D minus B times C. And that's right here. So here we have the determinant of our matrix. Cool, good eye. Does anybody know what A plus D is called? It's actually got a name. When you sum the diagonal elements of a matrix, my linear algebra friends, remember what that's called? Called the trace. The trace of a matrix is the sum of the diagonals. So this A plus D here is the trace of A. So given a matrix like this, the determinant is AD minus BC, and the trace is just A plus D, just the sum of the stuff on the diagonal. And that quantity shows up so much that we gave it a name. Otherwise, it's just silly to name it. Just make up all sorts of quantities and name them if you want. But this thing shows up a lot. So let's rewrite this equation. So to find, this is the big part here, to find the eigenvalues, let's values, we need to solve the characteristic polynomial. That's what this is. If you have more than a 2x2 matrix, this thing becomes worse. If you have an n by n matrix, n rows, n columns, that's an nth degree polynomial. The characteristic polynomial for us, check out this beautiful notation. It's lambda squared minus tau lambda. Tau's the trace. Plus determinant, which I'm going to use a capital delta for, equals 0. So here tau equals a plus d. Delta is AD minus BC. And that's just a pretty way to write it. You got the tau because T because trace. And the determinant, you know, D stuff. So let's play with this. So step 1 is find the characteristic values, find the eigenvalues. Let's go back to that matrix that I had at the beginning, and let's kind of work this through. So example, find the eigenvalues of, come back to this dude, 3, 2, 1, 4. So the first thing is I create this quadratic in lambda. Why don't you just go ahead and do that with me on your own. Make sure, and then look up this, or look up first. Whatever you need. Who's had it? Sick of this shit? And I would like to give you a few moments to please convince yourself, you already know the answers, but what are the eigenvalues? What are the solutions to that equation? It does factor pretty sweet, because it's rigged to factor sweet. Or quadratic formula is always your friend. Yeah, it's always your friend. Then, that's cool too. Just as long as you're at peace with that, You do what you need to do and want to do in this life, Lou, as long as you're happy. Beautiful. How are we feeling about this? Does that work? Can I answer any questions on this process so far? So we now know our eigenvalues. We know that there is scaling by a factor of 2 in one direction and a scaling by 5 in another direction. We don't know the directions, but we know that there's 2 scalings going on, and they are positive stretching ones. These are stretches. So this is a stretch by a factor of 2. This is a stretch by a factor of 5. Stretch. But where those happen, we haven't the foggiest. And we can't look at that, we can't look at the matrix and find this out. We have to go back to the original matrix. So now, once you find those, you're set up to roll on the rest of this process. And let me just make sure, is everybody cool with this? Does anyone need anything answered about that? Does that make good sense? Okay, cool. So step 1 is find the eigenvalues. We just did that. Done. Step 2. So now we have a little for loop. Good news, it's only got 2 possible things that it only has 2 loops it can make. For each eigenvalue, lambda, solve A minus lambda, C, B, C, D minus lambda. So that matrix that we started with, subtract lambda from the diagonal. That's all I'm saying here. Subtract lambda from the diagonal, and then slap on an xy here. And set that equal to 0. And we solve. For the x and y's, it makes this true. 4. Now here's the thing. You're going to get infinitely many solutions. All we need is one of them. We just need one solution to this and we're good to go, because we're looking for the description of a direction. And there's many descriptions for a direction in the plane, right? If I have 1, 2, that's also described by 2, 4. It's also described by -1, -2. So we just need one solution and we're solving. Just need one of the infinitely many solutions. God, I love this stuff. I just love eigenvalues and eigenvectors, because you take this matrix and you're really getting under the hood. You're really finding out, what is this matrix made of? We're about to find out a little more. So let's keep with our example. So our original example, so back to our example, take the matrix 3, 2, 1, 4, and proceed. So first, I like to organize my work like this. I'll take one of the eigenvalues. Let's start with 5. So lambda equals 5. And I subtract that off the diagonal. So off of the 3 and off of the 4. And what you're going to get is 3 minus 5 is -2. I'll put a little note here. That's 3 minus 5. That doesn't get touched. 1 doesn't get touched, but 4 becomes -1. So that is 4 minus the eigenvalue. And then I have that times xy. And that is equal to 0, 0. Can somebody help us solve this? What would you do? Trace it, yeah.
Do we do like -2, 2, and 1, and 0? Or
Ooh, can you say a little bit more about what you're saying there?
I guess I'm kind of putting everything into one vector. So it would be -2, 2, 1, and 0. And the bottom one would be 1, -1, 1, and 0.
I think we don't want to do that route. But I appreciate, that's good. That's did you yeah.
So you basically well, what I want to do is reduce the rows first.
Oh, let's not. That will actually change things. So that's a cool linear algebra thing to do. Oh, I see. You were going to go into. Oh, yeah, that would work. But there's something simpler we can do. So that would work. Here's the good news. You have 2 equations that say the same thing. Let's write this out. So look at the top equation. So Lou, definitely that plan would work. I take back everything I said at the beginning, but it's more work than we need.
Okay.
So check out this first equation. So we have 2 equations here. That's EQS. The first one is -2x plus 2y equals 0. And the second one is x minus y equals 0. Take a look at those and convince yourself they are the same thing. There's no new information gained. This equation, if you multiply it by -2, you get that equation right there. So you just need one of these. Let's go with the simplest one. X equals y. So this says the eigendirection is the direction where x equals y, the perfect diagonal. Remember how we first plugged in 1, 1 and got 5, 5? That's because it's on this direction. We put in -1, -1. We got up -5, -5. So we now know that any x, y we pick where the coordinates are equal works. So pick a sweet non-zero x or y value and find the other according to this equation. Accordingly, I'll just say accordingly. So let me start clearing up. This board's getting crazy. So any vector where x equals y works. And so what I'm going to say here is I'm going to make a little summary. Let's just put our little summary right here. We had lambda is 5, and I like to just keep my notes like this. I'll say is associated with the vector 1, 1. Why not pick 1? Make life easy. 1. It's a great place to have. Great thing to have. Could you now, my friends, find the eigenvector? You already know it, but let's find it together, corresponding to the other eigenvalue, which was 1. So now, do the same for lambda equals 1. So take your original matrix.
The other lambda was 2.
Was it 2? Thank you. Yes, thanks, Lou. That would have been a real cluster of some ilk. So here's your original. Subtract that from the diagonal. Figure out the solution it produces. This one really shows you that they're just the same two equations. Really get to see that here. Good. Got a bunch of fun stuff for us to do next. How's this feeling? Hopefully we're headed toward a vector that's in line with this. 2 to the left and 1 up, just like we actually drew at the very beginning. So this corresponds to this one. If you ended up, this is equivalent to the direction 2 minus 1. They're not the same vector, but they're the same direction-wise, right? So direction. And I got it. And I now understand what this matrix does to the plane. And so I want to show you how to put this together. If we come in this way, what is happening? Let me know, is there anything I can clarify? Anything that needs additional love? Okay. So here's what that matrix does to the plane. The original matrix, 3, 2, 1, 4, when I think of it as a transformation on ordered pairs x, y, it stretches away from the origin by a factor of 5 along the diagonal. So here's 1, 1, and along this 1, 1 right here, I have a factor of 5 stretching. So super stretching this way. I also have stretching along another direction. It's about half as much. So let's see if that's 1 and 1. I've got 1, 2, up 1. So along this direction, I have stretching by a factor of 2. Those are not indicative of, the magnitude of these doesn't reflect the actual stretching magnitude. But that means the plane, so imagine, you know, some demigod figure, some figure that can come in and stretch the plane, is pulling along this direction with maybe say a force of 5 newtons, whatever, pulling with a strength of 5 this way, but a strength of 2 this way. What does that do to the plane? Well, there's an app for that. You're gonna like this. Blah. All right. Oh my gosh, that looks really not on. How's that look? Living? All right, cool, sweet. Living. All right. Basically, to get to this app, I'll put this up in our classroom. I found this one literally moments before we arrived here, or you arrived here. So let's put our matrix in. 3, 2, 1, 4. Put that here. So 3. Jeez. Grandpa. 2, 1. Already 1 there. 4. Awesome. And now I think if I hit enter, it will do what I need. So I can, let's actually get rid of this and take the unit circle and see what's happening there. So imagine the vectors that have tips along the unit circle. This is what they become. So notice here, they have a magnitude of square root of 2 over 2, and then that gets stretched by a factor of 2. So it's literally 2 square root of 2 in this direction, that 2, 1 direction. And you can see the 5 pretty nicely, I think. You can at least see. But you can see the uneven stretching going on here. And so this is a great app. I really love this app. Let's take our eigendirections. So notice how, unless I'm on an eigendirection, the stretching is pretty weird. But the minute I get to my good old buddy, it clicked right in there. And so negative 2, 1 goes to negative 4, 2. It just got scaled by a factor of 2. No matter what I go in this direction, that's going to be the exact same thing that I see. That looks strangely, there we go. So negative 4, 2 goes to negative 8, 4. And then over on this side, notice how it's not mapping to the same direction, but close to it until I get right there. And then we've got 1, 1 going to 5, 5. So you're seeing this all around the plane. Now, what we could say, and this is what we will say, is that the origin here acts like a source. That there's stuff pouring into the plane through the origin, and it's pushing everything away. Think of like a white hole in the galaxy, right? It's just emanating. Not everybody knows what that is, I guess, but it's the opposite of a black hole, okay? You have some source, and it's pushing everything out. So this is a source, and that sounds familiar, doesn't it? We kind of did some stuff with sources, but we were doing it on the line. There are some other possibilities, and I'm going to let you discover them. We don't have enough time to go through all of them, but let me give you a couple other examples. Let's say I had 2, 1, 0. Let's see if we can actually maybe do this. Maybe we can do this on our own. Could you find, hey, let's just practice. Could you find the eigenvalues, please? I'll get it entered into our little buddy here. Remember your equation? It's that one. Lambda squared minus tau lambda plus delta is 0. If you've arrived at a place, that place should be -3 and 2 for our eigenvalues. And if you've got these eigenvalues, go ahead and find the vectors. Good practice. I see. Does anyone want consultation on these these values? Yes.
Did you do the thing where you like set it up so it's like a minus lambda?
So I would go straight to that equation right there, Tracing. The lambda squared minus the trace lambda plus delta plus the determinant. So much easier. You don't have to go through all that rigmarole. We were kind of deriving this formula. That's the money.
And that's always going to be the same.
Yeah, absolutely,
And
yes.
So to define the trace and determinant, I just do the boom boom.
Yeah. So what's our trace?
Is that this one here, or is it?
So the trace is this sum of this diagonal.
So then just -1.
-1 is the trace, yeah.
And then
It's
the
way
determinant-
better.
Yeah,
Yeah.
the determinant's the other side, right? So
Yes.
it's just 0.
N-
Or 1.
No. So the determinant involves both diagonals. So
Oh.
the determinant is the product of 2 times -3, -6,
And then just 0.
minus the 0. Yeah.
Gotcha.
Exactly.
Okay, that
Yep,
makes sense.
Yep. Good. Awesome. Well done. Nice. We all good here? Yep. That is solid. Yeah, absolutely. Hey, I just wanted to point out, you notice anything neat about the eigenvalues and the matrix? What do you see, Katrina? They're in the matrix. Here's a fun fact, useful tip. This is called a triangular matrix. If you have a 0 in the lower left or upper right pocket, the eigenvalues are on the diagonal. You can prove this to yourself, but if I have a matrix that looks like this, I've got A, B, 0, D, then my eigenvalues are A and D. Or if I have, or if I have this as well, A, 0, C, D, same thing. If you have a 0 in the upper right or lower left pocket, your eigenvalues, you can read them right off. That makes life easy, quick. So let's find those vectors. I don't know what they are. So let's see. Oh, that's neat. Oh, this will be fun. This might be, I can see how you might be feeling bafflement potentially at this point. What's that, Lou? Bafflement, yes. This one's kind of got a niceness to it. The lambda equals 2 has a pretty solution. Are we seeing this? Have we gotten here? Not yet. What, Cormac, did you get the vector yet for this one? You're not sure?
Yeah, I'm sure.
Okay, that's cool. Always, if you're not sure, if you look at the, I mean, so it's hard to read this stuff off unless you've been practicing a long time. Write the equations out. So the top one is 0x plus y equals 0. That says y is 0. The bottom one says 0x minus 5y equals 0. That also says y is 0.
Does it also say that 5y equals x?
Well, there's a 0 in front of the
No.
x, Lou, so yeah, it kind of vaporizes.
Oh, wait.
Does that make sense? Yeah?
I did something weird on my
If these equations don't say the same thing, you have done something weird. This is a little check, sanity check. If these two don't say the same thing, something terrible happened. I mean, terrible in math. Terrible in math is a great terrible. I'll take terrible in math over terrible in life any day of the week. So notice that we just get y equals 0 and x is free. It doesn't matter what x is as long as y is 0. So I'm just going to pick x is 1 and y is 0, and there's my eigenvector. As long as y is 0, I can't go wrong. As long as I don't put a 0 up here too. I mean, I could put, you know, a Google up there, and life is good. But I'm going to put 1 because that sounds sweet. And we can double check on this little app for ourselves. Let's see if if the x-axis is an eigendirection. So put a point. Let's draw it on here. I'll just move it out. And look at that. Notice how the vector 1, 0 goes to 2, 0. So that's saying I have an eigendirection here. The direction 1, 0 just got multiplied by 2. Stretching by a factor of 2. Oh, I knew that because that's my lambda. This tells me I'm stretching by 2 on the x-axis. Has anybody actually cranked out the other eigen? What'd you get?
I got 1, 5.
1, 5. Let's check that out. Let's try here. Let's try 1, 5. See what happens. I think we ought to look into that. Let's just see. But I love that you're going for it. The other one is going to be a negative. So let's do the eigenvalue for eigenvector for -3. Call it a day. So for lambda equals -3, I'm going to subtracting that off the diagonal amounts to adding it. So check that out. That's 2 minus -3. 1, 0. -3 minus -3. And so this top equation, and then that's times xy equals 0, 0. Getting a little crowded there. This turns into 5, 1. Oh, I see why you got that though.
It's -1.
Is that what the okay, got it. And then these are just, this just says 0, 0 across here. So the bottom equation is just 0 equals 0. Cool. Not helpful, but cool. We got it. We got that information. The top one is where all the good stuff is. It says 5x plus y equals 0. So I'm going to set y equal to 1 and find the x. Turns out x, yeah, I'm going to set x equal to 1. Sorry, I'm lazy because I don't want to do fractions. So if I set x equal to 1, y equals -5. So the eigenvector corresponding to -3 is going to be, the eigendirection is 1 minus 5. So let's check that out in the picture. 1 minus 5. All right. What's happening? Is this, did we get it wrong or is this okay? What's happening?
The eigenvalue is negative, so it flips over.
Exactly. The negativeness of it flips it over. So notice here that when I've got 1, -5, the output is -3 times this. So it's a flip over the origin. So this thing stretches in one direction, stretches in the other, but also flips around the origin. All right, friends, I could go on for hours. I could do this forever. I love this shit. But we gotta end. You gotta go to break. Have a great break. Some of you are here for another 75 minutes. Excellent. I'm gonna go grab my my tripod. Thank you.